If you were to crack open the battery that's powering your phone right now, which, by the way, please don't actually do that, you'd probably be a little underwhelmed. It's pretty much just a few feet of foil covered in a black paste, all rolled up tight. It looks surprisingly low tech, right? And yet, that simple little roll is, without a doubt, one of the most important inventions of the modern age. It powers everything from our laptops to electric cars, and even the satellites flying high above our heads. So, how in the world did this basic-looking roll of foil become the engine of our entire digital lives? Well, the answer starts way back, in a time when portable power wasn't just inconvenient, it was a roadblock. It was literally holding back the future. I mean, just look at the very first commercial cell phone from 1983. It took a whopping 10 hours to charge, and all of that for just 30 minutes of talk time. Can you even imagine? And this massive performance gap wasn't just a phone problem. Laptops, cameras, even crucial medical devices were all held back by these heavy, inefficient batteries. Everyone knew that whoever cracked the battery problem would unlock a whole new world. What they didn't know was that the first major clues had already been discovered. To really appreciate the breakthrough that was coming, we first have to understand this fundamental wall that scientists kept slamming into. It was a problem rooted in the most basic chemistry of how a battery works. So, okay, every single battery, even one you could make with a lemon at home, has three key parts. You've got the anode, which is the part that gives away electrons. Then there's the cathode, which, you guessed it, receives them. And finally, you have the electrolyte, in our case, the lemon juice, which lets positive ions travel between the two to keep everything balanced and the current flowing. But for decades, there was a hard limit on how much power you could get from this kind of setup. And that limit was a measly 1.23 volts. Why that specific number? Well, it's because nearly every commercial battery at the time used an electrolyte that was based on water. And if you tried to push more than 1.23 volts through it, the water itself would just give up. It would literally break down into hydrogen and oxygen. This voltage ceiling was the main barrier. To get more power, you couldn't just build a bigger battery. You had to smash right through this chemical wall. Now, our story shifts to the first innovator in this race, a British chemist named Stanley Whittingham. And the wildest part of this, he was working at Exxon, the biggest oil company on the planet, right as a massive energy crisis was about to shake the entire world. So in 1973, when the oil crisis hit and gas prices went through the roof, Whittingham's little side project on alternative energy suddenly became a massive priority. Exxon, afraid that its own oil supply might run out, started pouring money into his research. They basically told him to do whatever he wanted as long as it had nothing to do with petroleum. Whittingham's genius was really twofold. First, he used lithium. It's the lightest metal, and it has the absolute highest voltage potential. Second, he discovered a cathode material, titanium disulfide, that was built in layers. This structure was amazing because it allowed lithium ions to just slide in and out of the cathode, a process called intercalation. This made the battery rechargeable and stable, and it shattered that old voltage limit, delivering an incredible 2.4 volts. He had a working prototype, but there was a huge catch. To make it work, he had to use an anode made of pure metallic lithium. And that worked great right up until the moment it didn't. In fact, things got so bad that firefighters were called to his lab so often they threatened to start billing Exxon for the special chemicals they had to use to put out lithium fires. So why was it so dangerous? Well, every single time the battery recharged, the lithium wouldn't plate back on nice and smoothly. Nope. Instead, it would form these tiny, sharp, spiky needles. We call them dendrites. And you can probably guess where this is going. Eventually, one of those little needles would grow just long enough to poke right through the separator, touch the other side, and create a massive short circuit. The result? A fire, or sometimes a full-blown explosion. For all its promise, the battery was just too dangerous. Right around the time the oil crisis was ending and Exxon decided to shelve the project, Whittingham's research paper landed at Oxford University, and it fell into the hands of our second hero, an American physicist named John B. Goodenough. He saw the potential in that paper, and he just knew he could make it better. Goodenough had this hunch. The concept wasn't the problem, it was the cathode material. So he swapped Whittingham's titanium disulfide for a new metal oxide, and wow, the result was stunning. The voltage just jumped from 2.4 to a massive 4 volts. It was an absolutely incredible leap in power. But the real magic of his new cathode, which was called lithium cobalt oxide, was that it came preloaded with its own lithium. Now, this was the key insight. If the cathode already had all the lithium you needed, you didn't have to use that dangerous fire-starting pure lithium anode anymore. In theory, you could finally build a completely safe, high-voltage battery. He had the answer. A safe 4-volt battery was finally possible. But, and this part is just mind-boggling, when Goodenough tried to get companies or even his own university interested, nobody was. He asked Oxford to file a patent, and they flat out refused. Eventually, a government lab agreed to do it, but even they didn't really understand its potential. So for the second time, the lithium battery revolution was packed away in a box and left on a shelf to gather dust. The final, crucial piece of this puzzle would come from over 6,000 miles away in Japan. A chemist named Akira Yoshino stumbled upon Goodenough's forgotten research paper while, of all things, cleaning out his office. Yoshino took Goodenough's powerful cathode and paired it with a brand new anode made from carbon. And to prove just how safe it was, he set up a pretty dramatic test. He dropped a heavy iron rod on a battery cell that had the old, dangerous metallic lithium anode. It exploded violently. Then, he did the exact same test with his new carbon anode design, and nothing happened. Not a thing. That was the moment. That was when the safe, powerful, rechargeable lithium-ion battery was truly born. And from there, things started moving fast. Yoshino's company secretly flew the raw materials over to a tiny engineering firm in the US just to build the first prototypes. An executive then took one of those finished cells and, in a bit of corporate theater, dramatically rolled it across a conference table at Sony. The Sony execs were sold. And in 1991, they launched the world's very first commercial lithium-ion battery in their Handycam camcorder. But here's the absolute wildest part. Even after all of this, on paper, these batteries shouldn't have worked. During the very first charge, there's a side reaction that happens that really should just destroy the cell. But instead, something miraculous happens. It forms a super thin protective shield called the SEI layer. Now, this layer does consume a tiny bit of lithium, but it's the very thing that protects the anode and gives the battery its long, stable life. It's basically a complete, but very happy accident of chemistry. The combination of all these breakthroughs, the right materials, the safety, that lucky chemical accident, it all led to this. A 99% drop in the price per kilowatt hour of lithium-ion batteries since they first hit the market in 1991. That staggering price drop is what really unlocked the modern world, making everything from smartphones to electric vehicles affordable for all of us. But the story doesn't end there, because the incredible runaway success of this technology has created a whole new set of challenges and a really difficult paradox for our modern lives. So while the fundamental design is way safer than it used to be, the danger hasn't completely disappeared. Just think about this for a second. Every single week on an airplane somewhere in the world, a lithium-ion battery inside some device catches fire. This happens because of a scary chain reaction called thermal runaway. It all starts when that protective SEI layer breaks down, which releases a bunch of heat. That heat then melts the separator, causing a huge short circuit. Then the cathode itself starts to decompose, and when it does, it releases its own oxygen. All of a sudden, the battery contains everything it needs for a fire: heat, fuel, and its own oxygen supply, all trapped inside a tiny, self-destructing metal can. And this brings us right to the paradox of our charged world. While failures are statistically rare, about 1 in a million, we have billions and billions of these batteries out there, which makes fires pretty much inevitable. The resources we need, like lithium and cobalt, are finite, and their extraction has huge environmental and, frankly, ethical costs, with most of the world's cobalt coming from the DRC. And on top of all that, the future demand for electric cars and grid storage is just going to keep skyrocketing. You know, that incredible relay race of innovation that Whittingham, Goodenough, and Yoshino ran completely changed our world. But that race, it is not over, not by a long shot.
The hunt is still on for cheaper, safer, and more powerful batteries. They created the battery of our present. The question now is, what's going to power our future?